So our first talk in this session is Hyperreal specification for continuous sparse data computation with Vladimir Gladshtein. Please go ahead.
Yeah, hi everyone. Well, with the talk with a lengthy title, but what we're actually trying to do is simply verify these sparse data computations, not only sparse, also maybe some matrices which has repeated values and can be compressed, and yeah, so on and so forth. So more specifically, let me try to explain you what exactly do we want to verify. So imagine you have your data, which is like somehow structured vector matrix or tensor, and you compress it somehow, so such that you also have a operation, usually written, I guess, here as a Einstein notation, which you want to perform. So the kind of problem that we tackle here is how do we verify that given this efficient computation on the compressed data, it exactly implements the pure operation on the decompressed counterpart. So to tackle this, we develop a verification framework which allows for concise specifications, succinct proofs, and accommodates general structured data types like sparse, repeated values, and so on and so forth. And also in the end, I will briefly tell you about our current work. So we are working on generalizing our framework to also handle continuous data structures. Yeah, so let's begin. Yeah, here we present the framework called LGTM, which stands for Logic for Graceful Dense Manipulation. This is the outline, and first I will tell you how do specifications look like in our work. Then I will show you a small proof outline, and finally we will talk about our current work a bit in the end. Okay, we will look at a very simple kernel, which is the dot product of a compressed vector and a dense vector. You can see the sparse vector here, and we will compress it with two arrays, xval and xint. Right, so xint stores the indices of non-zero elements, and xval stores those non-zero elements. And then if we want to take a dot product, it's very easy, right? We just iterate through elements of the sparse compressed array, multiply them by the correspondent elements in dense array V, and then sum up everything together. So here is the very simple loop implementing this algorithm, and the same thing can be written using the mathematical notation, right? Well, the main question when you want to verify such computations would be how to represent formats in the proof. And the traditional approach would be to come up with specific memory layout predicates. For example, if we talk about the dense vector, usually all such kind of program logics, they have a predicate which says that, well, basically we have some pointer v, and it points to an array which payload of which is some pure sequence. And then to represent sparse compressed data, you actually will have to come up with some ad hoc predicate which says that, well, there is kind of decompressed pure sequence, and it is represented in the memory with xint, xval arrays. Once you've done this, you can, in your post condition, you can say that, well, after I run my function, I get a pointer, and this pointer points to the result written as the pure mathematical notation. So this approach was taken by the LA proof framework, and they verified the product of a CSR matrix and a dense vector. Well, that's how the representation predicate looks like for CSR matrix, and of course you need to understand separation logic pretty well to even read it. And also it follows by hundreds lines of format specific lemmas, which I needed to manipulate with this predicate. Well, which is fine, I guess, if you want to verify like one or two algorithms, but if we want to find a more general approach,
it would be nice to have like a simpler way to represent formats. Well, so what we do in our work, we realize that actually in some works and some libraries for sparse data, people represent those formats as code. For example, like in Finch, there is a special DSL which is to represent formats. And in general, you can implement just getter procedures, getter functions, which retrieve the value at the given index in a very simple linear search fashion. So those functions kind of tell you how does the format work, and you can actually use them to prove things. So I think everyone understands here how this function works, so I can skip it. And that was the first idea of our work. How about we try to represent formats as code? But then the question is, okay, how to actually prove anything about computations now if we represent formats as code. So to give you kind of understanding of the intuition behind our approach, let's briefly look at a more complicated example, which is the dot product of two compressed vectors. So here is basically the same code duplicated twice, which is the getter function for compressed sparse vector. And if you want to implement dot product in the two-finger merge style, the code will look like this. So it doesn't so you don't really have to understand what exactly is going on, but the idea is that you can see that the code for the dot product kind of incorporates some parts of the code of like for getters, right? Because basically the loop in this merge is in a sense a fusion of these two loops, right? Well, so our idea was to use a relational approach. So basically facilitate proofs by means of relating similar parts of the code and symbolically executing them in a lockstep. Well, now having all this in mind, let me explain you how we specify computations in our logic. So that was the old specification, and now we got rid of the predicate, but we still need to ensure that arrays, the encoding of the sparse array are somewhere located in the memories. That's why we leave them in our precondition. We abbreviate all of this as Rs. It's not super important. And now remember, we want to represent formats as code, right? So we'll have to go to the code section of the triple. And now, well, look at those xi's. Now they are not specified. So this is just components of the decompressed counterpart of our vector. And this summation mentions all of them, right, from 0 up to n-1. Of course, the majority of them are going to be 0, but we still have to specify them. So if we want to capture all of them, we'll have to run our getters on all indices from 0 up to n-1. And now it goes here. So now that's kind of how the triple look like. We will simplify it later, but for now, let me explain what does this triple even mean. First of all, this is a hypersafety specification because it relates properties of many programs. And now the idea is that we have these many runs of different programs and we run them independently. And when I say that we run them independently, that means that we run them on distinct memory heaps. So all those like heaps are equal. They assert the same predicate, but we just have different index for them. Now each getter will give you some element of your decompressed vector. And we bind all those results here to these variables x0 up to xn-1. And then we can use them in the post condition to specify our vector. All right. One thing you can notice is that the size of the triple is n+1. The arity of the triple is n+1, where n is the size of our input data, which means that n is a parameter. And LGTM is the first hyperlogic which deals with parameterized triples. So we had to develop a bunch of reasoning principles to facilitate our proofs. And now let me actually show you how roughly those proofs look like. Well, but before we even get there, we will simplify, we will do some notation for this triple to make it less hairy. So instead of writing all these getters one by one, we will just collapse them into a single line with the symbolic index I, which goes from 0 up to n minus 1. And now it looks a little bit nicer, I guess. Also, instead of specifying that this predicate R's holds for each copy of the memory heap, we just have this notation to assume that it holds everywhere. And we bundle all the outputs into vector x, which we use in postcondition to specify our pure vector. Well, the first step in the proof would be to get rid of all getters which correspond to 0 values in our vector. So to do this, we introduce a special rule in our logic, which is called focus rule. And we first split this set of getters into two. First one are those getters which we run inside x in the array, right, non-zero ones. And the second one are 0 ones. So we know we can basically kind of symbolically execute those getters and get 0. So that means that we will take this part of the summation which sums all this, like sums up all this value outside of x in the array and just replace it with 0. So our focus rule allows us to focus only on those components, only on those getters which we run inside x in the array. Now to proceed with the proof, we will have to remember that our algorithm is basically a for loop. And you can unroll it, and you will see that basically you iterate over elements of x in the array. So in the same way as you run your getters now only on elements from x in the array. Moreover, the ith iteration of the loop handles exactly the ith run of this getter. So we can bundle them together, and our logic has a rule which allows us to reduce the following goal to the simpler one, where you have to just prove that the pointer which accumulates your result will, after running one iteration and one getter, will increase by one element of the dot product. And this is the just a relational logic triple. It relates to programs, so you can prove it using standard relational logic techniques. All right. Now let me tell you about our current work. So sometimes you also want to work with kind of continuous data structures, right? So there is this extension of the Finch compiler to handle this. For example, you can have images, but such that it can be split into rectangles with the constant color. And one thing you want to do is to compute the average color in a unit segment, which is called interpolation. And well, you can represent this mathematically as double integration over the function which returns you a color. And well, you might want to verify such function. So to do this in our logic, you can still implement a getter using the same linear search. So this is not much different from sparse array and sparse matrices. And then our triples look like this. So the only difference is that instead of having this like line with symbolic index which iterates through finite number of indices, now it iterates through infinite number of indices through all the real numbers. So we had to kind of adapt our logic to well, have like all the reasoning principles to handle such scenarios. And this is like the ongoing work which we hope to release very soon. Yeah, now let's talk about evaluation. So we implemented and embedded all of that into Lean True Improver. So we wanted to see if those proofs actually are short and how do they compare to non-relational approaches. Well, this is our evaluation for our previous work, where we basically verified a bunch of discrete data structures like CSR, run lengths, formats, and so on and so forth. So the average proof code size ratio was just 2.55, which is quite good in the world of formal verification. Moreover, if you compare it to unary approaches, so we also verified the CSR matrix product with a dense vector, and our proof was just 36 lines of code, which is more than 10 times shorter than the unary Hoare logic approach. And also we have slightly less extensive experiments for our continuous extension. Here the proof cut ratio is slightly bigger because you have to deal with all these continuous operations like integrations and stuff, but still I think quite good. Yeah, I think that's it. So to sum up, I wanted to show you that you can use hypersafety logics to specify computations on sparse data. You can use parametricity to streamline proofs about loops, and finally reach up to 10x reduction in proof sizes compared to unary approaches. Thank you.